All right, good morning, everyone. Welcome to this general session on extremes. My name is Stephen Sobey. I'm with the Pacific Climate Impacts Consortium, and I'll be chairing this session. Just before we begin, I'm speaking to you from the University of Victoria, which is the traditional territory of the Lekwungen peoples and the Songhees, the Esquimalt, and Washanek peoples, whose historical relationships with the land continue to this day. So this morning we have 6 presentations lined up for us on various topics relating to extreme events in North America, and we'll get underway in just a second here. So I expect by now you're well aware of this, but just a reminder for our speakers that you'll have 12 minutes for your presentation, followed by 3 minutes for questions. And for anyone with questions, you're welcome to enter those into the chat in addition to asking them after the presentation. And so to start us off, our first speaker this morning is Alessio Spaziani. Hopefully I'm saying that right. And we'll be talking about wind extremes. So Alessio, whenever you're ready, you can take it away.
Thanks. Can you see my screen?
Yeah, it's clear. You're ready to
go. So yeah, I'm going to be talking about some of the work that I'm doing in regards to understanding wind extremes in Canada. It's a bit slow. Sorry, my screen doesn't want to change. Slide. There we go. So in Canada, we saw last year that $500 million in damage were a result of extreme windstorms. And just last month, we saw that major derecho event that went through Ontario and Quebec that caused widespread damage. And on the right here is just a picture I took from that event. These events cause significant impact on both infrastructure and people's lives. Unfortunately, not much attention is given to wind extremes specifically, and this results in higher uncertainty in both their historical trends as well as future changes. So there is this need to better understand the physical processes responsible for these wind extreme occurrences in both the current and future climates. So for this work, I'll be looking at using the hourly gust data that is available from the Digital Archive of Canadian Climatological Data. This data is available from 1994, but I'm focusing on the years of 1998 to 2020. And the reason for this is because I'd like to incorporate lightning data at some point, and that data is available from 98. Here we define extreme gusts as those greater than 90 kilometers per hour. And currently, I'm focusing on the areas around Vancouver, Toronto, and Montreal. So these figures show the location of unique station IDs, and those are represented by the red dots. And locations are chosen if there's at least 10 years of gust data available, and whether that is using one station ID or multiple station IDs. So for example, in Hope, BC, we have, there's 8 points, and the shading here is the number of points within an Era 5 grid cell. So Hope has 5 unique station IDs, and a couple of those stations experience a change in their lat and long throughout their record. Stations that are around complex terrain are avoided, and this is to minimize the effects of topographic influences on measured gusts. So for our 3 regions, in Vancouver, we have 9 locations that use 14 station IDs, and 54 extreme gust events are observed. In Toronto, we have 14 locations, 21 station IDs are used, and 161 extreme gusts are observed. And in Montreal, we have 7 locations, 9 station IDs, and 16 events. So these figures here just show the number of events observed between 1998 and 2020 within an Era 5 grid cell. One important limitation to note here is that we don't make any correction for events that occur but are not observed by the sparse network of stations. So this will result in a bias in our observational data that we don't account for currently, but hopefully in future work, that's something we might be able to correct. So on top of the observational data, I'm looking at using reanalysis data. So we're using the Air 5 data, and specifically for this work, again, looking at 1998 to 2020, the current spatial domain being considered is 30 degrees north to 90 degrees north and 160 degrees west to 30 degrees west. And for now, I'm looking at the 850 hectopascal temperature and specific humidity, and I'm using these to calculate the 850 equivalent potential temperature, and I do this using the MetPy Python library. And then the data is split into the 4 different meteorological seasons. So here, just give you an idea what this data looks like. This is the median theta E at 850 anomalies for our 4 seasons. So the approach I'm looking to use is self-organizing maps. This is a type of machine learning that is able to classify large volumes of data. So in our case, the hourly AR5 data into a 2D grid of map nodes. So for example, here, we have a 3x3 SOM, so we have 9 different map nodes. So this is an iterative process where the input data is repeatedly compared to the vectors of each node. And these vectors are initialized randomly, and then they get updated based off of the input data assigned to them. There's also a parameter associated with the SOM called the neighboring function, and that allows adjacent nodes to also get updated to some extent. The benefits of this approach compared to other approaches that look at analyzing spatial modes, such as empirical orthogonal functions, is that it doesn't assume orthogonality and it doesn't assume stationarity. So what that means is we're able to get patterns that are more physically relevant, as well as the SOM assumes the data exists on a continuum instead of discrete categories. To run my SOMs, I'm using the SUSE Python package. And just a very simple kind of example of how the SOM works. Let's say we have our input data here at some time t. The SOM will then calculate the best match unit to each node's vector. And this is typically done using Euclidean distance. And then, so let's say this input data is assigned to this node. This node's vector will get updated based off of this new information. And then this is done for the entire data set. So I've only just begun to get some results from these SOMs, so it's still pretty preliminary. To keep things simple, I just wanted to look at one atmospheric variable for now. So I chose the 850 theta E. And the reason for this was because it's a decent metric for defining air masses, since it incorporates both temperature and moisture. So unfortunately, I haven't done much analysis with respects to testing the performance of the SOMs. And because of that, I'm not going to get into much detail of what's being physically represented by the different nodes. But just kind of want to show you an idea of how the results from the SOMs can be incorporated with our observational data to try to make connections. So if we look at our SOM here, this is a 3x3 SOM for spring. And we can see that the SOM appears to be well organized in that in the top left corner, we have this strong negative theta E anomaly. And as we move down and across, we see how this pattern slowly shifts. And in the bottom right corner, we have the opposite of a strong positive theta E anomaly. The SOM also keeps track of the data assigned to each of the nodes. So above each of the subplots, you have this number, and this tells you the number of data points assigned to that node. So the data isn't going to be evenly distributed amongst the nodes. Some nodes are going to have more data, other nodes are going to have less data. So so since we can keep track of the data assigned to the nodes, we can see where our observed events fall as well. So on the right here, these are our event counts for our 3 regions, Vancouver, Toronto, and Montreal for the spring months. And if we just kind of focus on Toronto, since it's a bit easier, we have a lot more events observed in Toronto. We can see the majority of our events fall within these 3 nodes. So where we have this strong negative theta E anomaly over Canada and North America. We then get some more events occurring in this node, and then a few events occurring where we have the strong positive theta E anomaly. So the idea is to try to then try to understand the relationship between where we're getting events and what the atmospheric setup is being explained in the nodes. So there's still a lot of work to be done. So I've just started getting those results. So the idea is I want to expand to other atmospheric variables beyond just theta E. So I want to try to kind of develop some kind of weather map over North America that would best explain the occurrence of extreme winds in different parts of the country and for different times of the year. I also want to look to separate synoptic events from convective events, and this is where the lightning data would come into play. So the idea would be that a convective event would be defined if there's lightning occurring around the time and around the vicinity of an observed event. I also am looking to expand to stations across Canada. So there's about 1,500 unique station IDs that have some amount of hourly gust data available. Those need to be quality controlled to check for locations that have at least 10 years of data and to remove any erroneous data as well. So I've probably gone through about 500 of those stations. So there's still a lot of work to do with respect to that. And the idea would be to then group stations into different regions. So one possibility would be these Bukowski regions as shown in this figure here. And then the good thing about the SAW method is it can be quite flexible. So we can then incorporate different global or regional climate models into our SOMs to try to get an idea of which patterns or atmospheric setups are becoming more or less frequent under different climate change scenarios, according to different models, to try to understand how the occurrence of these events might change for different regions of Canada and for the different seasons. So yeah, thank you for listening.
Yeah, great. Thanks very much, Alessio. So if anyone has any questions for Alessio, feel free to enter them into the chat or raise your hand. So while we're waiting for some potential questions, I just had one. You mentioned that there can be a mismatch between the gusts that you see in the ER5 data and the station data. I'm just curious how frequently that happens.
Sorry, what do you mean the gusts seen in the ER5 data?
Or one of the original slides, I guess at the start, it sounded like you said there was sometimes you didn't see the same gusts in the station data that you saw in the gridded data.
Maybe I misspoke. I haven't looked at the gusts within ER5 yet.
Or maybe it was one of the, yeah, I think it was when we were on this slide. You were mentioning there was some.
So I'm just, was it talking about gusts that occur but may not be observed by the network?
Yeah.
Yeah, so I just mean like the network's pretty sparse, so you're not gonna pick up every event by the station. So the observational data is gonna be biased to what the stations are able to observe.
Okay.
Sorry, that's what I meant.
Okay, no, thanks for that. So at the moment, I don't see any other questions or any other raised hands. So, so if anyone does think of any questions, feel free to enter them in the chat. But at this stage, we can move on to our next speaker. So, Melika Rahimovagar, if you are ready to share your screen and get going, we can get started here. All right, great. Yeah, whenever you're ready.
Can you hear me well?
Yeah,
and you
we can hear you.
See my slides. Yeah.
Yes.
Thank you. So, hello everyone. My name is Melika Rahimovagar. I'm a PhD candidate in the Department of Civil and Environmental Engineering, Western University, and I'm presenting this talk on behalf of my research team, which is titled Spatiotemporal Patterns of Successive Dry and Wet Spells over Canada. We have a number of different examples of floods and drought in Canada. I have picked two examples. One is the 2013 flood event in Toronto, and the other one is 2001 to 2002 drought event in Saskatchewan. For which the first one, like the drought event, had 126 millimeter of precipitation. It closed multiple transportation, caused widespread property damages, affected approximately 300,000 residents, and almost $1 billion of damage. The drought event had affected 41,000 people, agricultural products, and people's employment, crop and livestock production, and almost 5 billion economic loss. So these were the individual events. So what if we look at the consecutive or the successive dry, wet, and wet, dry events? In the literature, there are a number of those cases, which the most well-known one is the case of California, which the Oroville Dam, second largest reservoir in the California's spillway, was completely damaged, as you can see in the figure. And it was as a result of, because first there was a drought during 2011, 2016, and then an extreme precipitation event occurred in 2017, and suddenly they couldn't manage, and those collapse happened. And we also have the wet dry events. An example of it could be the Mississippi River, which in 2011, 2012, 4 billion flood event ended with a 30 billion drought event. So our objective for this research is first to assess the lagged compound wet and dry spells characteristics, including frequency, magnitude, and transition time, and also to evaluate the spatial and temporal patterns of these successive events, and to identify the hotspots for the abrupt and non-abrupt cases, and also to investigate the effects of low frequency variability modes on these compounds. So in the methodology, first I have to talk about the characteristics of those lagged compound events, dry, wet, and wet, dry events. The first characteristics to go over is the transition time, which will give us the case of the abrupt and non-abrupt case. Transition time means the time between the end of the first event and the start of the second event. And if it's less than 30 days, we'll call it an abrupt case, and it is less than a year, we'll call it a non-abrupt case. So having that in mind, frequency is the number of the events per year, and then magnitude is basically an index that we adopted based on Lee et al. 2017, and now it's based on the magnitude of the wettest spell and driest spell, which is calculated based on the standardized stream flow series unitless. And so the thresholds here to calculate the driest spell is the Monte quantile 20, and to calculate the wettest spell is quantile 90. And this is the equation that we have used, is the same for the case of abrupt and non-abrupt case, only the name is different. So to see the effect of the low frequency variability modes, we have used the Bayesian quantile regression. We have used two of those low frequency variability modes, which is one of is the multivariate Enzo index MEI, and the second one is the Pacific North American pattern PNA. We assess the effect of these telecollections on the lagged compound characteristics of the both wet dry and dry wet event, including the frequency, magnitude, and transition time. Also, when we apply the Bayesian approach, it allows us to quantify the uncertainties in the estimates. And since we have some gauges with low number of the observation, it is really critical to use this method. A study area is the whole Canada, including the 13 territories and the provinces. Our data is based on the RHBN, Reference Hydrometric Basin Network, and Water Cycle of Canada stream flow gauges. We did some pre-processing. We only chose the gauges that had less than 10% of missing data during our study period, which is 1963 to 2012. We also deleted the gauges which had more than 4 years of consecutive missing years. It ended up with 164 RHBN gauges and 104 WSC gauges, which is in total 268 stations. And we also downloaded the monthly MEI and PNA time series from the NOAA website. I will then move to the results. So then first I'm showing the some spatial maps of the characteristics of those lagged compound events versus the frequency of the abrupt case of the dry wet event. If you look at the map here and those red circles and ovals, you can see that because the higher values of frequency based on the legends are more purple to dark blues, they are mostly occurring in the coastal areas, which includes the west and east coast and southern Ontario in the Great Lake region. And when we switch from the abrupt case to the non-abrupt case, the red oval on the west will extend to the whole BC. For the case of the abrupt wet to dry event, we can see the same spatial pattern. And when we look at the transition time of the dry wet events, you can see that the lowest values, which are basically the most important for us, are occurring again in the coastal areas, west coast and east coast, and also the southern Ontario in the Great Lakes region. And this is the same case for the wet to dry events. And moving to the magnitude of events, this is the magnitude of the wet dry. The top figure is the abrupt case, which again you can see that the highest values are first occurring in Ontario, southern Ontario, and then in the west and east coast. And when we move from the abrupt case to the non-abrupt case, you can see that the spatial pattern will completely change. And now the lagged compound events are occurring in the basically Alberta region. And then the dry wet spell is basically the same maps with same characteristics. When we pick the starting month of those events, you can see that first for the Canada, which is the black thicker line, is mostly occurring on May, which means that the dry wet and wet dry compounds are mostly starting for most of the gauges in Canada on May. The pattern is different for different provinces, but mostly you can see that they're higher, the number of events are higher from March to August for the dry wet, and the same applies to the wet dry event. So when we are looking at the influence of low frequency variability modes on abrupt dry wet spell compounds of frequency, if we pick the right figure and then the case of Ontario, you can see that, and now we have plotted the mean regression slope based on different quantiles. You can see when the quantiles gets higher, the slope is also getting higher, and also there is a negative relationship between the NEI and then the abrupt dry wet frequency. And then it's obvious that it becomes more pronounced at larger quantiles. And so when we look at the case of the PNA, you can see that for Ontario, there is not much significant effect based on PNA on the abrupt compound dry wet event. When we switch to the magnitudes of the dry wet event, again picking Ontario as the province, and then looking at the MEI, you can see that there is a positive relation between MEI and the abrupt consecutive dry wet magnitude. And then when the quantiles are getting higher, in higher quantiles or extremer occasions, you can see that there is higher slopes, which means that the relationship is becoming stronger. This is also the case for the case of the PNA, but there is a negative relationship between the PNA and the abrupt compound dry wet magnitude. And so when we switch to the wet dry magnitudes, you can see that in the case of Ontario, higher quantiles, like there isn't much significant effect based on MEI on the magnitude of the abrupt wet dry event. There was higher in the effect on the lower quantiles, which is the same effect on the based on the PNA. You can see on the left figure. And when we pick the frequency of the wet dry event, you can see that again, in the case of Ontario, there is a negative relationship between the MEI and also the characteristic, and the quantiles are getting higher. In the extreme case, there is more relationship between these two, and which this is not the case for the PNA. And in the higher quantiles, there is no relationship between the considerable relationship between the PNA and the characteristic. So in conclusion, I have to say that overall, the climatology of the lagged compound dry wet and wet dry spells show consistent spatial patterns. Coastal areas show the highest frequency of lagged compound event and the lowest transition time. The magnitude of such events is also higher in coastal areas, but the magnitude of the sorry, there's a mistake here. The abrupt case is higher in the coastal areas, and the non-abrupt case, it is correct in the the central regions. The total number of the dry wet spells is less than wet dry spells, but this is not the case for their magnitude, and we can say that the magnitude of the dry wet spells is higher than the magnitude of wet dry spells, and also the impact is higher, as we can remember that severe case of the California reservoir. The low frequency variability modes of MEI and PNA can influence the lagged compound wet dry and wet dry events, but the behavior is completely different based on different regions. So for the most regions, the influence of those low frequency variability modes is more pronounced at higher quantiles. The observed dry wet and wet dry spells have implications for water and disaster risk management, especially across the coastal zones for Canada, as we saw those figures. And in the end, I have to acknowledge our foundings and also my supervisor, Dr. Najafi, and thank you for your attention.
All right, great. Thanks, Melika. So if anyone has any questions for Melika, please feel free to enter them in the chat or raise your hand. So while we're waiting for people to maybe type those in, I'm curious, there looked like some strong relationships for places like PEI or others in the effect with the PNA or the MEI. And is that just because of a small number of stations, do you think, or is there a strong relationship there as well?
So the stations were not small in all provinces. Actually, in Ontario, I think we had almost at least 80 gauges. So when we take into account 80 gauges and then find those results, it must be some sort of relationship really happening there.
Right, okay, great. We have a question in the chat from David. Have you thought about incorporating precipitation observation networks such as COCORAS into your analysis? There are several stations available in the prairies. Yeah,
so our study is mainly based on a stream flow. Basically, the compound dry wet and wet dry analysis are done based on different variables. They have mostly been done based on precipitation, but less on a stream flow. And in this study, we wanted to see what will happen if we pick a stream flow and then do our analysis based on it. Yes, we sure could do it based on precipitation and then see what will happen. Yeah.
Great. And then just one last question. Is all the flow data natural flow? Did you use all flow data?
Yeah, they're all natural gauges.
Okay, great. All right, thanks, Malika. So I guess we'll move on to our next speaker, which is Ting-Chen Chen, who will be talking about extratropical cyclone wind speeds. So whenever you're ready, Ting-Chen.
Thank you. Share my screen.
All
Okay.
right, great. Yeah, see your full screen.
Okay. Can you see the cursor as well?
Yeah, yeah, we can see that too.
Okay. Hello, everyone. I'm Ting-Chen Chen from the University of Quebec in Montreal. The work I'll be sharing today is about the seasonal variations of near-surface wind speeds associated with extratropical cyclones over northeastern North America. Extratropical cyclones, or ETCs, is a major contributor to severe high wind events, but past studies have mostly focused on the winter season because that's when the large-scale ETC activity reaches the annual maximum. However, on the local scale, ETC activity may exhibit different seasonal characteristics. For example, in a list of the top 10 intense windstorms in northeastern United States, published by Lesson et al. 2021, we noticed that 8 out of 10 actually occurred in spring and fall seasons, while only 2 occurred in wintertime. And for Eastern Canada, a famous example of ETC with strong winds in fall is the Halloween storm in 2019. During its passage, multiple provinces in Canada recorded wind gusts exceeding 100 kilometers per hour, which led to downed trees, power lines, and one of the biggest power outage in Quebec. So the main goal of this study is to explore the seasonality of ETC associated near surface wind speeds, and then based on the results to derive a simple formula for ETC wind assessment. And we target the continental region over northeastern North America. This region is influenced by high frequency of extratropical cyclones as primary continental cyclone tracks merge here in almost all seasons. And on top of that, the Great Lakes and Hudson Bay are both hotspots for ETCs as they provide enhanced heat fluxes. All the analysis conducted here use the ERA 5 hourly reanalysis from 2000 to 2020. And to identify cyclone tracks, we first performed an ETC tracking algorithm developed at UQAM over this large gray shaded region. And then from all these track cyclones, we further select a total of about 1,400 cases that have impacted this targeted region for at least 24 hours. So for each of these sub-selected case, we calculate its associated 10-meter wind speed by taking the spatial and temporal averages over an 800-kilometer radius circular region around the center, and also over its duration in the study region. The same spatial temporal averaging is also applied to different fields to investigate how the seasonality of 10-meter wind speeds is correlated with that of other variables. And to determine whether the distributions between any two seasons are significantly different, we apply the two simple Kolmogorov-Smirnov test at 1% significance level. So first, let's take a look at the seasonal distribution of ETC-associated 10-meter wind speed as shown in the left panel. They are expressed in standardized values. So values larger than 1 are considered severe as it exceeds the mean of all cyclones by 1 standard deviation. First of all, the ETC 10-meter wind speed are found to be significantly different between any two seasons. And the 10-meter wind speed is notably higher for cyclones in the fall season from September to November. And since the most direct driver to the near surface wind speed is the synoptic scale circulation of the cyclone, for that we also examined the wind speed at 850 hectopascal, shown in the upper panel. And from this box plot, we do see that the median of 850 wind speed is also the highest in the fall season, but the difference among fall, winter, and spring at 850 hectopascal level are not found statistically significant. And overall, 10-meter wind speed is positively and actually highly correlated with 850 wind speeds as expected. But if we take a closer look at the number of cases in the upper two quadrants of this scatter plot, we will find that the fall season, colored in yellow, actually show the highest number of severe cases in 10-meter wind speed, no matter whether the 850 wind speed is severe or not. And so from another perspective, among all ETCs that exhibit severe 10-meter wind speed over this study region, about 38% of them actually occurred in the fall season, while only 26 and 24% occurred in spring and winter. So to understand the inconsistency of wind speeds at two levels, we examine another variable that is the low level stability, measured in terms of the bulk Richardson number. A lower Richardson number indicates a less stable air layer, which favors stronger near-surface winds because turbulence mixing could result in a larger vertical momentum transport from the free atmosphere into boundary layer. We calculate this ETC-associated bulk Richardson number for the two lowest ERA 5 model levels. And overall, we do see a negative correlation between 10-meter wind speed and Richardson number. And furthermore, we can see that the relative seasonal variation of Richardson number and 10-meter wind speed are reversely consistent. This confirms the importance of this variable in modulating the seasonality of 10-meter wind speed of ETCs. And to obtain more insights, we further decompose the Richardson number into two subcomponents. One average over the land surface and the other average over the inland water surface. And it is clear that these two subcomponents exhibit contrasting seasonal variations as their dominating stratification term. And this is due to different heat capacities among water, ice, and land. I'd like to draw your attention to the yellow box plot. This is for the fall season. We can see that the ETC-associated Richardson number in fall remains relatively low over land, but even more so compared to other seasons over water surface. And an additional factor that helps this characteristic is because the ice cover generally reaches annual minimum during SON season. And so more open water areas with substantial heat fluxes can lead to a weaker stratification above. The next critical factor we also examined is the surface roughness, as shown in the leftmost panel. The seasonal variation of ETC-associated surface roughness is generally consistent with the areal fraction of land surface covered by each ETCs in different seasons. So summer and fall ETCs have lower land surface fraction because these ETCs favor water surfaces, especially the Hudson Bay when there's low ice cover. The seasonality of this variable is not always statistically significant, but overall there is still a moderate negative correlation between surface roughness and 10-meter wind speed as expected. So finally, we use all the three previously mentioned variables, including the driving winds at 850 hectopascal, low-level Richardson number, indicating low-level stability, and surface roughness length to derive a simple formula for 10-meter wind speed prediction based on the ordinary least squares linear regression. And we can see that the fitted formula shows a good prediction of 10-meter wind speed, the overall root mean square error is about 0.42 meter per second, and the correlation between the predict and observed 10-meter wind speed is as high as 0.95. And the importance of including this Richardson number and surface roughness is highlighted when we compare it with the linear regression model that only consider the driving wind at 850 hectopascal. The root mean square error increased from 0.42 to 0.78 by 46%. And so with this formula, we can further quantify how much each of the predictor variable on the right-hand side contributes to the seasonality of 10-meter wind speed. So we did this by computing the seasonal mean for each term in this equation. And so we can, for example, conclude that compared to the winter time ETCs, the higher 10-meter wind speed in fall over this region is 30% attributed to the higher driving winds, 41% to the lower stability, and 29% to the lower surface roughness in fall compared to winter. So to sum up, extratropical cyclones over northeastern North America exhibit significantly stronger 10-meter wind speeds in the fall season compared to other seasons. And the reasons are, there are three reasons found responsible. First, continental ETCs in this region are slightly stronger with slightly stronger driving winds at 850 hectopascal in fall. And second, most importantly, the low level stability is significantly lower in fall compared to other seasons, and this favors downward momentum transport. And finally, because cyclones favor the Hudson Bay during the low ice cover season, these cyclones experience lower surface roughness than those passing through the land surfaces. And using these three variables, we can derive a simple formula that will predict the 10-meter wind speed and the seasonality associated with extratropical cyclones. So especially would like to highlight that the low-level stratification of surface roughness should be considered in ETC wind damage risk assessment and may be useful for trend analysis for climate studies. One last thing to mention, our ETC data and analysis will be publicly available soon. So if you're interested, please feel free to reach out. Thank you.
Great, thanks very much, Ting-Chen. So if anyone has any questions for Ting-Chen, feel free to put them into the chat or raise your hand. So one question maybe while we're waiting is just, have you looked at how any of these driving factors change over time, over long-term time beyond the seasonal scale?
We focus on like the present climate for now, so we haven't really looked into the trends, but that's definitely something that worth investigating for the future.
Great, and we have a question in the chat. So intense fall ETCs in Atlantic Canada are often related to decaying tropical cyclones. Have you looked at that potential factor in ETC strength?
For tropical cyclones?
I believe, yes, in the question there.
Yeah, so actually in our tracking algorithm, we search for low, the minimum mean sea level pressure at cyclone centers. So the algorithm itself actually did not exclude tropical cyclones. And of course, the majority of the track cyclones are extratropical because the target domain is in mid latitudes. But we didn't differentiate between mid latitude and tropical by adding any other constraint for the study.
Great, and we have another question. So the highest observed wind speeds deviated from your line, and do you have any plans to address the more extreme winds in different regions? And Minnie says, great work.
In different regions?
Yeah.
So far we actually we don't plan to do that, but I definitely think this simple linear regression master can be applied to other region. It's not our plan for now.
Okay, great. So yeah, if anyone has any further questions, feel free to enter them in the chat, and Tichen can follow up there. So we do have a scheduled break with the next speaker to start at 9:20 Central Standard Time, and we don't have any posters for this particular session. So I guess we will reconvene in about 10 minutes time for the next speaker, but we'll leave the session open until then. So we'll see you in shortly. All right, good morning, everyone, and welcome back to the second half of our first morning session today. We'll now begin the next of the three talks with Michael Morris, who will be discussing Canadian wind extremes. So whenever you're ready, Michael, you can take it away. All right, great. Yeah, we can see you.
Oh, yeah, sorry. Yeah, great. Sorry, I was just going to unmute myself after sharing the screen. But yeah, it's all good?
Yeah, everything's
Great.
clear. Thanks.
All right, awesome. Thank you so much. All right, yeah, so as mentioned, so the title of my talk is Canadian Extreme Wind Events in Models and Reanalysis. So kind of similar to Alessio's talk, my work focuses on extreme winds in Canada, but then I, of course, looked at these in both reanalysis as well as how they're represented in climate models. Yeah, so I'll go through the motivation quickly. So of course, as Alessio mentioned as well, extreme near surface winds are a natural hazard with a major societal impact in Canada. They can cause, costly damage, such as is, depicted in this image from the extreme wind event that happened in where I live in Toronto recently, a couple of years ago. So of course, this is a convective extreme wind event, but yeah, you can see there's, damage to homes and vehicles due to fallen trees, power lines, things like that. I think there were some people that were without power in the Greater Toronto area for several days afterwards. So of course, these are an important, natural hazard for us to understand. So in addition to understanding them in the present day, it's important to understand how extreme winds may change under climate change for the purposes of adaptation. So we have a collaboration with some folks in structural engineering, and of course they're interested in how design wind speeds and the building codes might have to change for the purposes of the resilient tall structures. So to answer the question of how these extreme winds may change under climate change, we'd like to be able to use climate models to study how climate change will affect extreme winds, as these are the tools that we normally use. Excuse me, I advanced too quickly, but these are the tools we normally use to study the effects of climate change. Unfortunately, climate models have biases in near surface wind speed. So this is illustrated here in this in these fitted Weibull distributions of 10-meter wind speed that I've taken from a few different products. In black are from the weather station observations at Pearson Airport. In blue is from a free running climate model, so the CSM large ensemble, which has a resolution of about 1 degree by 1 degree. And then in green from the AER5 reanalysis for the same location, which has a high resolution of about 1/4 degree. But you can see in both of these model derived products, the right-hand tail, where the extremes are of this distribution, is a lot heavier in the observations than in the model. So these models are sort of underrepresenting these extreme winds. So one question that we're asking then is, if the models aren't simulating the near surface winds themselves well, might there be still something, excuse me, I'm sorry, not sure why that's advancing. Might there still be something that we can learn about these near surface winds from the other, perhaps more well-resolved larger scale variables, excuse me. So in other words, the main research question that I'm asking are, what are the large scale drivers of extreme winds that can be well represented in climate models? So in order to study this, I'm going to bridge information from station observations, reanalysis, and a free running climate model to examine the scale and the character of these extreme wind events. So what I'd like to do is first to be able to use the AER5 reanalysis to produce composites of some large scale fields to look at the large scale structures of the atmosphere during these extreme wind events. But of course, first we need to ensure that these extremes that we're selecting actually show up as extreme winds in the reanalysis as well, or else we may not be getting the right relationships between the large and local scales. So what I've shown here are scatter plots of wind speed, where on the x-axis is from the station wind speed from each of these different 7 major cities in Canada, and then the AER5 wind speed on the y-axis. So in each of these data sets, there are multiple stations that I've used within each city to try to categorize a similar sort of area to the typical scale of the AER5 grid cell that covers the area around the city. So we can see that for each of these cities, AER5 captures about half of the observed extreme winds, and the threshold that I'm using for the extremes is the 98th percentile wind speed. But fortunately, it seems like if you just focus on some of the absolute strongest events, which of course may be those that have the greatest impact and might be most important for consideration for design or adaptation, it seems like that percentage tends to increase. I used an independence criterion to focus on these extreme events, so that you might notice some very high wind speeds that are grayed out, that are not shaded like an extreme. And that's simply because those extreme events occurred within a day or so of another extreme wind event And so since I'm later going to take composite averages over the events, I didn't want to have, sort of one longer extended extreme event have too much influence in the synoptic pattern that shows up. I'll also mention here that I'm focusing on extreme wind events only in the winter, spring, and fall seasons. I noticed that overall the winds in the summer season were much weaker. So I excluded them from the data set, and they wouldn't really show up so much in these top 2 percentile wind speeds anyway. Right, so I've made some composites of a couple different large scale variables, excuse me. And what I've done is, in addition to just focusing on these extreme wind events in each of these cities, I've also separated these extreme wind events depending on the local wind direction. And one thing that I have found is that these synoptic patterns differ with the local wind direction. What I've shown here is just the most predominant class for each city. So like, for example, in Montreal, 78% of these observed extremes were from the southwesterly quadrant, which is quite a huge percentage, whereas for Halifax, for example, the largest was 35% in southeast. And so I have composites for all the different wind directions. I just wanted to show the most common to show the sort of typical event that you've seen here. So these are composites of the 300 hectopascal wind speeds from ERA 5, and we can see this jet streak pattern embedded usually in the trough of a Rossby wave at a synoptic scale. And so we can see that these local wind extremes are matched with jet streaks at upper levels. And this shows that while these extremes are happening at the surface, there are indeed dynamics in the free troposphere that are governing them. So jet streaks are known by, in the meteorological community to provide a favorable environment for extreme or severe weather. And this is by inducing vertical motion through their pattern of upper level divergence. This promotes things like deep convection as well as cyclogenesis near the surface. So just really quickly, I'd like to show this, the velocity potential associated with these upper level wind speed patterns. So where it's negative, that's where there's strong divergence. And you can see also in this divergent wind field, there is strong upper level divergence that results in a reduction of mass in the column below. So like I said, can promote cyclogenesis near the surface. And as we know, the extratropical cyclones can be associated with strong winds. But it can also promote convection, as I mentioned, which is important for wind extremes as well. So this is what I've done with the ERA 5 reanalysis. And next what I wanted to do is to see how well a free running climate model that doesn't assimilate any information from observations can reproduce the same sort of patterns that we've seen in the reanalysis for the observed historical events. So I've done this for 2 different flavors of CESM, the Community Earth System model. First, using the CESM large ensemble, which is a set of 40 independent, fully coupled realizations of the 20th and 21st century climates. I've just focused on the 20th century portion, keeping in line with studying historical events like I have in the reanalysis. And this model has approximately 1 degree resolution globally, I think, as I mentioned before. I've also performed some of my own simulations using a variable resolution configuration of CESM. And so this has approximately a 1 degree resolution around most of the globe, but it refines incrementally down to about 7 kilometer resolution right in this, right in this region of the finest resolution. So slightly different from the CSM large ensemble, this is just a AMIP style simulation that I've done with time slice forcing. So the same boundary conditions, radiative forcing, sea surface temperatures and sea ice, which were prescribed from the large ensemble. So I've done 30 years of this time slice simulation, like I said, only with the atmosphere and land models, using prescribed sea surface temperatures and sea ice concentrations, but taken from the CSM large ensemble. So it's meant to mimic the same kind of climate period. And it's of course shorter because it's a much more computationally expensive simulation to run this very high resolution. I wanted to highlight a couple of areas in particular where this variable resolution model has shown improvements relative to the coarser resolution CSM large ensemble. So what I've shown here are sea level pressure composites, which I've also done for ERA 5. So for specifically extreme events in Toronto, since that is one major city that falls into our region of very fine resolution, and the top row shows the composites from ERA 5 for sea level pressure, the middle row from the CSM large ensemble, and the bottom row from the VRCESM, and from these 2 different wind direction classes. So for the southwesterly events, which is the predominant wind direction class in Toronto, it looks like that the composites are pretty similar for each case. So we see this strong sea level pressure minimum, indicative of a cyclone propagating near the city. And both the coarse resolution large ensemble as well as the refined resolution VRC-ESM produce pretty similar results there. So this is encouraging to see that even the coarse resolution model is able to well capture the sort of dynamics, the synoptic dynamics at least, that are associated with these extremes. But there are these less common event classes, so these northeasterly winds in Toronto. And this is one area in which the refined resolution really added value relative to the coarser resolution large ensemble simulation. So we can see this sort of tilted high-low pressure dipole pattern and associated with these northeasterly extreme wind events. And if you orient yourself with the pressure minimum on your left, so then you'd be facing in the direction of the geostrophic wind, you see that the geostrophic wind for these events is more southeasterly rather than northeasterly. So there must be some strong ageostrophic processes associated with these northeasterly wind extremes. For the large ensemble, it seems like this pressure dipole pattern is oriented a bit more north-south compared to how it is in ERA 5. But when we look at the locally refined resolution model in the VRC-ESM, it seems like we get better representation of these ageostrophic processes because the sort of relative position of these high-low pressure relative to the city, which is marked by this red dot, which I should have mentioned, it aligns better with the ERA 5 reanalysis. So it really seems like refining this resolution can help represent these ageostrophic processes. What I've shown here are Taylor diagrams for the sea level pressure during the extreme wind events for both the large ensemble and VRC-ESM. So if you're not familiar with these, essentially, so this essentially shows the level of agreement between the overall pattern for the model composite and the composite for ERA 5. So the ERA 5 has perfect correlation with itself. And so the correlation is sort of shown by the angular coordinate here. And of course, its standard deviation ratio with itself is 1. So the radial coordinate on these Taylor diagrams is the ratio of standard deviation, and the angular coordinate is the correlation. We can also then, as a function of these, write the root mean squared error. And so these sort of semicircle contours here show the root mean squared error between the pattern for the CSM composite and ERA 5. So essentially looking, going from left to right is where we go from coarse to fine resolution. And we can see that overall these composites, so for the different cities and with the different wind directions, for the refined resolution model tend to have lower root mean squared error. So they're falling mostly in this lower contour and seem to have high resolution. They're clustered more closely together. And that's indicative again that there are improvements that are seen in this refined resolution. One thing that's also promising is it looks like that the model's still performing poorly in the same areas. So for these Vancouver northeasterly events, it seems like a pretty poor job is done by both the large ensemble and the finer resolution VRC-ESM. But if you'll notice at the grid, Vancouver is well away from our region of the finest resolution. So there isn't very much greater resolution compared to the large ensemble. And so there isn't really anything that's seen that's different. So that's actually kind of an encouraging result to see, is that where we don't expect there to be a big change, there still isn't a very big change. I'm running low on time, so I'll try to go through this quickly. This is, again, highlighting another way in which the refined resolution model adds value. And essentially, we see in these in the CSM large ensemble, for example, for these southwesterly Toronto events, a lot weaker jet streak wind speed than we saw in ERA 5. It's still a bit weaker in the VRC-ESM, but it does seem like it's able to simulate, a stronger relationship between these strong jet streaks aloft and extremes at the surface. And that's something that we didn't really expect to see, because we expected that at upper levels and sort of at this with these very large scale characteristics, to not see so much refinement with improvement with the refined resolution. But it does seem like that even for these synoptic patterns in the free troposphere, there is some improvement offered by the refined resolution. I've done a bit of digging into that, and again, I'm running low on time, so I'll try to go very quickly. But essentially what I've done is I've tried to check to see if there are indeed strong jet streaks similar to what we saw in ERA 5 in the model, and if it's just that perhaps in the CSM, the sort of vertical coupling between the jet streaks aloft and extremes at the surface isn't quite as strong as it should be. So one way I've done this is I've calculated pattern correlations for these upper level wind speeds in this box around the city to essentially select times in the models where they're during any time, so not just during extreme winds at the surface, but to find when there's optimal agreement with the ERA 5 composite. Then what I've done is plotted the distribution of the surface winds during these times. And I've done this both for ERA 5 with itself as well as the models with ERA5. So at the top are showing here the observed wind speeds during times when there's maximal agreement with the ERA5 correlation. So I call that when there's a strong jet streak, because of course during those times are when there are these strong jet streaks. And then I've done it again for the model. So this orange distribution are the surface winds during the strong jet streaks in CSM large ensemble, and then the blue is the distribution during the extremes. Then what I've done is integrated essentially this area overlapping between these two distributions in order to get the conditional probability of an extreme wind event, given that there is a strong upper level jet streak. And so I've done this for both the large ensemble and VRCSM. And so we can see that for cities like Toronto and Montreal, where in the ERA5s and observations, there seems to be a pretty strong connection between these upper level jet streaks and extremes. So conditional probabilities of 20 to 30% nearly. They're severely underestimated in the coarse resolution version of CESM. Whereas when we go to refined resolution, this connection between the upper levels and the surface is falls closer to this 1-to-1 line. So it's a lot closer to what we see in the reanalysis. And so that suggests to us that this refined horizontal resolution is actually helping us better capture some of the vertical connections between the upper level dynamics and the extremes at the surface. So I've gone a bit over time and I apologize for that. So I'll just leave the my conclusions here, and yeah, I'll take some questions if we've got time.
Yeah, thanks, Michael. So there's a question in the chat, but I'll ask you to address it there in the interest of time so we can move on to our next speaker. So thanks, Michael.
Great, thanks.
So our next speaker will be Mohamed Ali Benalea, who will be talking about precipitation extremes in downscaling. So whenever you're ready, Benalea, you can begin.
Yeah, thank you so much.
All right, we can hear you.
Can you hear me now?
Yeah, we can hear you. Don't see any slides yet.
Yeah, okay. I'm gonna show my screen. Okay. Okay, can you see my screen?
Yeah, all good. Take it away whenever you're ready.
So good morning, everyone. I'm Mohamed Ali Benalea, Research Associate at Pacific Climate Impact Consortium. Today I'm going to talk about evaluation of BCC-AQ for downscaling precipitation extremes using large ensemble regional climate simulation and a high resolution convection permitting model. So this work is a part of a Global Water Future Project climate-related precipitation extreme project. So in my work, I'm going to handle two main concerns: one general concern and another specific concern. So for each concern, I'm going to present data and methods and results, and then I will conclude. So in Canada, the principal source of downscaling future precipitation is statistical downscaling using BCC-AQ, the bias correction constructed analog with quantile mapping reordering version 2. So the downscaling procedure consists of calibrating the BCC-AQ using climate model simulation over a historical period and calibrate this with high resolution gridded datasets, and then apply the calibrated transfer functions to future climate model simulation to obtain future higher resolution gridded datasets. So a key assumption to do so is to assume that the BCC-AQ transfer function will not change under future climate conditions. The key concern is that this assumption cannot be tested because we lack future observations. However, one option is to test it using in a perfect world. So to handle this issue, we're going to test this in a perfect world. We're going to use daily precipitation over southern British Columbia. We use we use CAN-RCM for, we will try to downscale CAN-RCM for regional climate models to work regional and forecast models at a convective permitting spatial resolutions. So CAN-RCM is 50-kilometer resolution. It was developed by Environment and Climate Change Canada, Canadian Center for Climate Modeling and Analysis. So the WRF simulation that we use was conducted by Yan-Ping Li and her team within the Global Water Future project. So for WRF simulation, we're going to use historical control simulation that cover the period from 2001 to 2014, and future pseudo-global warming that correspond to the expected climate over at the end of the century. So in the procedure that we used to test the stability of the BCC-AQ transfer function in a perfect model work. So first, we're going to take a member from the CAN-RCM4 large ensemble over the historical period, and then we calibrate the BCC-AQ transfer function using the available CTL-WRF simulation. Then we're going to apply this calibrated transfer function to the same member to obtain a higher resolution downscaled results. And then we compare this with the control WRF. Now for the same member, we're gonna take the same member over the future simulation and apply the same calibrated transfer functions to obtain high resolution data over the future, downscaled data over the future. And then we're gonna compare with the pseudo-global warming WRF simulations. Now we're gonna take another member from the CAN-RCM4, but this member is not used to calibrate the BCC-AQ. It is an out-of-sample member, and to obtain, and then apply the BCC-AQ transfer function to obtain a high resolution data sets, and then compare with WRF. We're gonna take the same thing for the member 2 over the future, apply the BCC-AQ transfer function to obtain future higher resolution data, and then compare with pseudo-global warming simulation, pseudo-global warming WRF data. So now we're gonna call the in-sample member that is used for the calibration ESM. Well, the member that is not used to calibrate the BCC-AQ, we're gonna call this out-of-sample member. So in our comparison, we're gonna focus on precipitation extremes, mainly on annual maxima. So we're gonna repeat this process again using other members, ISM2 and OSM2 member. We're gonna repeat this again and again, and 50 times. We're gonna repeat this 50 times to build knowledge about the impact of internal variability on downscaling evaluation and performance. I show here now, when we move to the result, I show here some example of the downscaling result for mean of annual maxima. We can show here this is the CAN-RCM4 using the ESM member, and here is the downscaled result. This is the CAN-RCM4 for the OSM members, and we see the downscaled results here. So for the OSM1 results, we see that precipitation is a bit larger over the mountainous regions, and the BCC-AQ was able to downscale this successfully. So the result for mean of annual maxima was very good. For the standard deviation, the results are performance are a bit lower, but in general, BCC-AQ provide good, exhibit good job. We can see, for example, here, the effect of a single event for the standard deviation. And this is mainly because the period is really very short, even though we try it in our approach to take account of information from nearby location by using a bootstrapping approach that help us to inflate the sample size to 70 years. Here we show that the percent bias of mean of annual maxima from the 50 downscaled precipitation series using the 50 OSM and the 50 ISM of CAN-RCM4 simulations for the control and the pseudo-global warming period. So we can see that for both ESM and OSM, the performance over the control period is substantially better than the performance over pseudo-global warming period. So the result for the relative root mean square errors of mean of annual maxima for both the 50 downscaled precipitation series using the in-sample member and the out-of-sample member of downscaled results, we can see that the performance over the control period is also better than the performance over the pseudo-global warming period. So now we turn our attention to specific concern. And here we need to investigate the potential of the BCC-AQ to generate unprecedented precipitation extremes under present and future climate circumstances. So to do that, we will propose an extreme value-based likelihood ratio statistics. So let's take X1 represents dwarf precipitation annual maxima, and X2 is BCC-AQ version 2 downscaled annual maximum. So to assess the ability of BCC-AQ to predict unprecedented precipitation extreme, first, the BCC-AQ, it is necessary that BCC-AQ reproduce the mean of annual maximum. So mu1 and mu2 represent the mean of annual maximum. However, this is necessary but not sufficient. The mean is not, this is not enough. And it must also reproduce the variance of annual maximum. But to reproduce unprecedented extreme, this is also not enough. And he must also reproduce the rate at which largest value get larger. And we assume that this parameter that quantify by how much largest value get larger is represented by a shape value. So the BCC-AQ to reproduce unprecedented event, it must reproduce that rate. And to obtain this 3 parameter, they can be obtained by fitting a GV distribution. So the GV distribution here can be considered as the skeleton of the body of extremes. So if you take a 2 body of extremes, if the 2 body are similar, then the skeleton must be similar. But if the skeleton of the body of extremes is the same, this is not necessary. This is not necessary that the 2 body will be exact. So here it is necessary that to reproduce unprecedented extreme, it is necessary that BCC-AQ will reproduce the 3 parameters. It's necessary, but this is not sufficient. So to take that, we take the hypothesis. The null hypothesis is that the 2 parameters are equal, and the alternative hypothesis that the 2 parameters are different. For the likelihood ratio test statistics, it's compare the log likelihood of our data under the basic model compared to the log likelihood of our data under the hypothesized model. And theta hat here show the MLE of theta 1. We take X1 and we fit a GV distribution, and then we take X2 and we fit the GV distribution using the MLE. So here, this is the general model where X1 and X2 can be similar or different. And then we calculate the log likelihood of our observations under the hypothesized model. Theta tilde represents the hypothesized model. Emily, here we take X1 and X2 and we assume that X1 and X2 have share the same GV distribution, and we fit theta. So what is the statistics? We need to know what is the statistics of D. General D follow a chi-square distribution with degree of freedom K minus Q, where K is the number of functionally independent unknown parameters in the basic model, and Q is the number of functionally independent unknown parameters in the hypothesized model under H0 is true. So in our case, we do have 6 parameters under the general model, 2 GUV distribution to be fitted. H1 have 3 parameters, so we have K equal to 6. So when for the hypothesized model, we assume that X1 and X2 share the same distribution, and in that case, we do have only 3. So the degree of freedom of our statistics is going to be equal to 3, because we have 6 functionally independent unknown parameter in the basic model and 3 functionally independent unknown parameter in the hypothesized model. So here I show the result of the p-value for the pseudo-global warming and control periods using H50 ISM and 50 OSM downscaled precipitation annual maxima series. we can see that over the control period for ISM, the p-value is very large, which is good. So for the out of sample member, the p-value, it's a bit lower than the control period, but typically performance is not good, is not really so bad. However, over the pseudo global warming, we see that the p-value is very slow, very low. So if we present here the rejection percentage of rejection at a 5% significance level. So for the ISM in simple member, we see that over the control period, the percentage of rejection was 5%. So this percentage increase when using out of sample members, and the value was the percentage of rejection was 16%. Over the pseudo global warming period, we can see that the percentage of rejection is approximately 51% in both ISM and OSM out of sample member. So in conclusion, BCC-AQ downscaled results agree with the target WRF simulations over the calibration periods. On the other hand, performance were substantially lower when operating in warmer future conditions. But in conclusion, we should think a little more deeply about the impact of using a transfer function that can be affected by warming signals and how to reduce its related bias. So thank you so much.
Great, thanks, Malaya, for that presentation. If anyone has a quick question, I think we have time for one. So from Dail, can we apply a simple bootstrap approach for the significance test?
No, we did. Actually, we didn't apply a bootstrap approach for significance test. We only used the bootstrap approach to inflate the length of our data record. A bootstrap approach that account for additional information from nearby location.
Okay, great, thanks. So if there are any further questions, feel free to enter those into the chat. Then I can take care of them there.
Yeah, thank you so
much.
much.
Now, yeah, thanks. We'll move on to our final speaker for this session, who is David Sills, who will be talking about tornadoes and hail. So whenever you're ready, David, you can take it away.
Okay. Shut off this meeting panel. How's that look?
That looks good to me. Yeah, you can see your slides and we can hear you fine. So whenever you're ready.
Need to get to the first slide. There we go. Okay, so good morning all. And this presentation is intended to provide an update on the Northern Tornadoes Project and also introduce the new Northern Hail Project. And so I'll be presenting the first half, and the second half will be presented by the new Executive Director of the Northern Hail Project, Julian Brimlow. So the Northern Tornadoes Project. So this has turned out to be a severe weather community endeavor, really. NTP was founded by Western University and Impact WX, which is a social impact fund out of Toronto, back in 2017. We have a core team that's composed of meteorologists and wind engineers, and led by myself and Professor Greg Kopp, who's the research lead. And we also have strategic partnerships with the University of Manitoba, and you can see John Hanisak on the side there, the Weather Network, Instant Weather, CatIQ, and also we closely collaborate with Environment Canada. So the objective of NTP is to advance the knowledge of true tornado occurrence and risk across Canada. So what we want to do is detect, assess, document, and make public all Canadian tornadoes. So it's ambitious given Canada is such a big country, but we've been covering the entire country now for since 2019, and it's gone pretty well. So we're getting great data. The data can be used for climatology, for risk assessment, climate change baselines, and other uses. There's also research that improves and sets out to improve or automate event detection and assessment, both in forest and prairie lands where it's hard to detect tornado occurrence. And that's done with an external research team that's made up of scientists from the US, the UK, and Canada. So just to provide an update of what happened in 2021 with NTP, we conducted 401 investigations. So many reports come to us and we conduct investigations on them all. But those investigations resulted in 291 actual events. And you can see the event types on the right side here. A tornado over land, 81, tornado over water, 19, 95 downbursts, 44 non-tornadic vortices. So these might be dust devils or gustnadoes. And 52, there wasn't enough evidence to provide a classification. And you can see that all those events stretched from the Yukon all the way to Nova Scotia. If we just look at the 100 tornadoes, again, 81 over land, 19 over water, you can see most of them were concentrated in Ontario and a few in Quebec as well. In fact, there was the one fatality due to a tornado across the country was in Quebec at Mascouche, just northeast of Montreal. But you also notice that really it was very quiet on the prairies, and I'll go into that in a bit. So just some extremes from the 2021 season. We had the first tornado to hit Vancouver since 1976. Both the one in 1976 and the one in 2021 were after EF0. You can see a photo of the tornado as it was over the ocean, and thankfully it dissipated somewhat before it hit land. It occurred in November, so very rare, both hitting Vancouver and occurring in November. On the other side of the country, the first Nova Scotia tornadoes, 2 of them since 1999, and the strongest Nova Scotia tornado since at least 1980 at EF1. Again, I said it was very quiet in the prairies. There was actually no tornado damage registered or reported in Alberta. We just had 3 EF0 default tornadoes, meaning they were visually confirmed, but there was no damage caused. And this is the really interesting one. There were no tornadoes north of the 49th parallel across Canada between mid-June and mid-August, which is the 60-day period with the highest tornado frequency in Canada. So really unusual that there were no tornadoes across that entire region through that period. We also had downburst damage in the Yukon, rated EF1, and Northwest Territories rated EF2, and that was associated with the big heat dome out in BC. As I said, lots of Ontario tornadoes. We actually had a record number of tornadoes in Ontario, 60 in the province, 46 in Southern Ontario, a record number of F or EF2 plus tornadoes, which 16 was the number there. All of them were EF2. Thankfully, none were worse than that. And another very late season tornado in Ontario at November 21st near Newmarket. And I'll be giving a talk a little later about how our tornadoes seem to be moving in later in the season. And some other NTP news. We did the first ever independent tornado warning performance assessment. So that can be found on the NTP blog. And we're aiming for an atmosphere ocean paper on that. We're completing long-term databases and climatologies, and Francis will give a talk on that this afternoon. We're working on analyzing trends in the long-term record, and I've got a talk on that this afternoon. Also work on advanced interactive NTP dashboard. So we have a dashboard now where you can look at all the events, but we want to do something more advanced, a second dashboard. And this will have tornado track plotting, events going back to 1980, and more filtering options. So more advanced functionality. And lastly, we're collaborating with Instant Weather on a new community radar processor and viewer. And that should be available for beta testing soon. And we're going to continue work on that with severe weather algorithms that will be open source and hopefully contributed to by the public. And that's it. I'll hand it over to Julian to finish out the presentation.
Great, thanks very much, Dave. So I'm excited to speak to you today about the Northern Hail Project, which is a new initiative out of West University. in Ontario. So some of you might be asking, well, what is the Northern Hail Project? And in a nutshell, the Northern Hail Project is a project aimed at advancing the meteorology, climatology, and impacts of hailstorms in Canada. And the ultimate goal is to improve data that people have access to. So we hope to have benefits to Canadians, municipalities, businesses, and other stakeholders. So for example, insurance companies who are wanting to develop risk models. The approach we decided to adopt for this, for the Northern Hail Project, is we've identified 6 basic tasks, main tasks, and it's from the ground level up, so it's data driven. And you'll see here in this pyramid that task 1, for example, is collecting hail, measuring its size, the amount of hail, and collecting information on hail swaths. And then number 2, we're looking at the aerodynamics of hailstones. So the reason that's important is that when a hailstone is falling, its fall velocity and ultimate impact energy is determined by the aerodynamical forces acting on that hailstone, and that's pretty constrained right now. And we're also going to be conducting, for the first time, urban and rural hail damage surveys. There's no real playbook on that. There is a playbook for tornadoes, but we don't have anything yet for hail. And ultimately, those data are going to be pulled into a national hail event archive and climatology, and I'll speak to that on the next slide. These data are also going to feed into some numerical modeling of hailstorm environments. That's in task 5, and then task 6, we're going to be looking at hail hazard modeling and vulnerability modeling. So that's obviously very important and something that the current climatology, if one could call it that, it is not able to do. Just a quick note to some of the collaborators and partners we'll be working with. So this work's being done in conjunction with ICLR, Instant Weather, ABIHS out of the United States, and WeatherLogics out of Manitoba. We're hoping to train a whole bunch of grad students. Right now, we've earmarked 10 PhD trainees, 7 MSc trainees, and we'll be employing almost 40 summer interns. Next slide, please. So I don't have time today to speak to all those tasks, so I'm just going to highlight one of them. And that's documenting all damaging hail events across Canada, and using those data together with proxies. Canada's just too big to rely on reports, but using those data with proxies to develop a national hail climatology. And other goals will be to detect and assess and document new hail events as they occur across the country. We've already started with that this summer. We want to develop a comprehensive new national hail climatology based on recorded events and the proxies. And one of the challenges we have is that we're using social media a lot. The problem with that is the photographs, as you can see on the right-hand side there, are not always presented in a manner that allows us to provide an accurate estimate of the hail size. So we're hoping to use some machine vision techniques to attempt to derive some useful information from those photographs and include them in our database. And then, as with the NTP, we hope to share all these data through a public-facing data portal that will be updated every year with annual reports. And over the course of the 5 years of the project, we hope to have sufficient amount of data to present a climatology, at least a preliminary one. Next slide, please. So NHP activities. This summer, we're starting a pilot campaign. The field team are already out there. They're in Red Deer, and we actually conducted our first mission the other day on Sunday, and everything went successfully, so I was very excited. We're doing this work in collaboration with the insurance companies in Alberta, and we're planning a 5-year field project. So we're initially starting off in Alberta because that's where we guarantee the best success. It's a good place to learn, but from then we're going to expand farther west and east across the country to document all the damaging hail events. So primarily, we'll be looking at operational activities for now, as is the case with the NTP. But of course, this is also going to be research driven, and we hope to include data from a portable test bed that I'll be speaking to in a couple of slides here, so we can have a holistic picture of everything going on. So as I mentioned before, right now we're looking at collecting as much data as we can. So we have a dedicated field team. This year, it's just one small field team, but in successive years, that's going to grow, and we'll have more teams to deploy. And they'll be going in and close to hailstorms and severe hailstorms to collect data. So we'll be collecting information on stone diameter, weight, shape, density, hardness, and also documenting information on the hail swath, depth and width, and taking multispectral imagery from UAVs. And that stone on the right there would be a beautiful example to do some 3D scanning and printing that we're hoping to do. So we'll be getting a scanner in the fall to do some scanning of the stones. Next slide, please. So just the timeline here, this is very rough. Don't hold us to this. It's very much a work in progress, but this year we're also in a very exciting development, going to be deploying a distrometer, a hail distrometer network in the city of Calgary. It'll be the first such network in an urban area in Canada. And we, like I mentioned earlier, we have that field team out there collecting data over Hill Alley. This fall, we're hoping to enroll the first graduate students at Western and University of Manitoba. Next summer, we're hoping to do fully field operations and damage surveys, both in urban and rural environments. And we'll be using some exciting technology there, like LiDAR. Then in 2024, 2025, we hope to collaborate with IceChip, which is an initiative out of the States where they're going to be looking at hailstorms in Colorado, Nebraska, and Kansas. And we'll also be expanding our fieldwork farther afield. And then in 2026, we're hoping the first PhDs will finish, and then we'll be wrapping up around the winter of 2027, 2028. Next slide, please. So I did mention earlier this portable test bed in Alberta. This is a really cool project that we're working on getting funded right now. We'll be assembling hardware that we've managed to procure from various sources, including Environment Climate Change Canada. So the big part of this is dual pole Doppler C-band radar. We've got a lightning mapping array, surface weather stations, hail pads, hand tilt cameras that we'll have deployed in the field to get real-time observations. We'll have mobile mesonet units, and we'll also be deploying or releasing weather balloons. And this is all to determine a holistic picture of hail and tornadic storms to improve the detection of them and to improve and test nowcasting methods. Next slide, please. So just to summarize, as Dave mentioned earlier, the understanding of Canada's national tornado climatology is improving a lot as the NTP endeavors to detect, assess, and document every tornado that occurs in Canada. And if you want more information, you can go to the NTP site at the University of Western Ontario. They have some great tools and data portals there. And the new NHP will also be using cutting-edge technologies and techniques to improve hail climatology for Canada. You can go to the NHP website, but I do warn you right now it's under development, so there's not much there, but we hope to populate that and expand upon it in the coming weeks and months. And I think that's it. Thank you.
All right, great. Thanks, David and Julian. So we have one question in the chat. Has any consideration been given to using AI techniques on satellite data to help with the tornado event detection?
Yeah, actually quite a bit of consideration. We've had a number of students try to do this, and it's really a difficult thing. What we want to do is be able to know that areas have damage, and then we want to know how many trees are down, what percentage of the area has down trees, which direction are they down, these kinds of things. So these are the areas that we're working on to trying to use AI to do this. And we're getting there. It's difficult. I'm hoping we'll be able to have something like an 80% solution so that it's a good first guess. And then the last 20% is done by our teams. And that would certainly alleviate a lot of the tedious work that people are doing right now. But the 100% solution is certainly several years away, if not more. So it is something we're working on, though.
Great. And for Julian, would CocoRAS being crowdsourced hail information, would that be helpful?
Oh, definitely. We are planning to work closely with CocoRAS and to leverage those data and to any other partners who might be able to share data with us. So yes, is the short answer.
All right, and our last question from Mindy, what improvements do you have planned for use of our radar and remote sensing for hail size estimates, especially where we have attenuation problems and confusion with heavy rain?
Well, the latter point may be mitigated somewhat by using the S bands. They're not as susceptible to attenuation as the C bands, but nonetheless, that is still a problem. We are going to be relying on space-based techniques as well, and surface-based techniques. And right now, you may know that differentiating between hail size is problematic, even with the dual polarization radars. And we're hoping to develop or improve some existing techniques that allow us to better differentiate between hail size. And that might mean using a combination of dual polarization data and conventional radar data. And that hasn't been looked at too closely, but ultimately we need really good ground truth data if we're going to develop any new tools. And that's what we'll be doing when we're collecting hail out there.
All right, great, thanks. And so that concludes, I think, our session on extremes this morning. I just want to thank all of our speakers again for their excellent presentations. Thanks everyone for attending and for your great questions. And thanks to Chris for running the technical aspects of this session. So with that, I think we'll end there. And the next session will be the plenary at 10:30 Central Standard Time. So thanks again, everyone.